actually trivially easy to scale. So that, for example, I have a list of, let's say, 1,000 elements. I'm currently computing that on my one-core computer. But let's say that list becomes a list of 1,000,000 elements or 1,000,000,000 elements. I can split that list across servers or across threads, across servers, across processes. And that'll be really trivial because I'm letting the programming language handle that for me. Also, it's arguably easier to conceptualize and understand. I said arguably because this comes at a cost of understanding some functional principles, some of which we'll cover today. But yeah, they're actually way easier to understand. And I would dare say that when you're looking at someone else's code base, if it was coded in a functional manner and you understand functional principles, the learning curve to picking that language up and that code base up is actually much more minimal. So, next slide. So the key points of functional code bases that we'll cover today, I don't know if you guys could see this, is that we can use functions for everything. We're going to avoid side effects. Data is immutable, meaning that I wouldn't change any variable that I have. I wouldn't change any arrays that I obtain. You might think that by doing this, it's impossible for us to make any meaningful program, but we'll show you tips and tricks on how we can work against that later on. And also, we're going to be avoiding statements that we've seen in C-style programming languages, like if statements, and instead we're going to be focusing on expressions. If you notice, there's like a cheeky acronym here, spells out fade, but that's nothing. You guys can use that to remember this if you want to remember it, but you don't have to remember it. So next slide. So functions for everything. So what does that mean? That means that functional programming, instead of thinking in classes and objects like object-oriented programming languages like Java, you instead switch your thinking into functions. And the fact that the functions you create could possibly obtain functions, and they could possibly return back functions. So it's basically like an inverted thought process. Also, the more complicated functions that you want to build, you build those more complicated functions by composing simpler functions together. So let's say I have this element and I want to multiply 5 to this element and add 6 to this element. Multiply and add are two simpler functions that you can compose together to build out more complicated functions. And again, we'll show examples of that. So let's switch to an example. This is a simple example in Haskell of putting this principle into practice. So let's switch back to the previous slide. So the principle of functions for everything. So if you notice, let's switch to the next slide. If you notice, I have this complicated function called validate, and this is actually a credit card validator. I'm getting some credit card number, and I want to get back a Boolean. So, by the way, in Haskell, this is what you call a type signature. So I have a type signature here, and a type signature here. A type signature is kind of like what you have with types in Java. All I'm saying here is that I'm receiving an integer array. I'm receiving an integer array here. I'm receiving an integer. And my function that I created is returning back an array of an integer. In here, I'm returning back a single integer. And in here, I'm returning a Boolean, which is true or false. So I have this very complicated credit card number validation process. I don't know how I could possibly create this. So instead of putting all of the logic of credit card validation in this one function, I instead break this up into two simpler functions that make it up. So there's a sum digits function. All this sum digits function does is it receives a list of integer. So let's say I get a list of numbers, right? A list of 1, 2, 3, 4, 5. What this function would do is it would add that list up together to some result. Whereas this one would actually double every other integer in that list. And that's what I'm using to create this more complicated function. Is anybody lost at this point? No one's lost. So I don't want you to understand Pascal is a functional programming language. I only want you to get the principle that I have this more complicated function, but I'm using this very simple function and this very simple function to create the functionality that I want to see happen in this function overall. I'm composing, if you notice, I'm using some digits here, and I'm using the double every other function here. And the way that this flows is I have CC number. CC number is an integer, so then that means I have the, I didn't define it here, but there's a 2 digits function somewhere, and that 2 digits function returns an integer. And since double every other receives a list of integers, what 2 digits does is it converts the number that it receives to a list of, what do you call this? List of numbers. So let's say I get a string of 110, it turns that into a list of 110. And the logic basically flows into like that. So I just want you to get that higher level overview. I don't get bogged down with the details of this. Avoiding side effects. So side effects is anything that happens outside of the programming language. So anything from displaying graphics or rendering HTML, changing data from the database, printing out text, so doing like a system out print line, and listening to keyboard events, when a user clicked on the H key or the G key. You want to avoid doing those things as much as possible. And if you are doing them, you want to restrict them to one portion of your code base, a part where you can easily inspect where everything is happening. So let's switch to a quick example of this. This is in Python. I don't know if you guys could see. Can we zoom in possibly? Let's zoom into router py right now. I think we can do a command plus. So command plus, we can zoom into router, so left, yeah. So this is a very simple Python application. So in this Python application, all I'm doing is kind of like what we did in our Node.js workshop. We're creating a router. We're basically building a server. And in this server, whenever I hit this login URL, all of this happens. So I'm obtaining the username that the user provided. I'm getting the password that the user provided. And I'm doing some complicated operations. Now, my code base, my inner code base, the part of my code base that actually handles the logic of validating a user's login, it shouldn't care about the fact that I have a server, or it shouldn't care about the fact that this may potentially be in a desktop application. It should only worry about the fact that I'm getting some username, I'm getting some password. I want to validate that, check if that user exists in my database, and if they do, return a true or a false. And if the validation is successful, return some kind of JSON web token back. That's exactly what's happening here. So the cruft of the login logic actually happens within this login function, and all of the logic concerning making a backend server is relegated to this function. So is anybody lost at this point? No one's lost at this point. Okay. So if we switch to the next code base, so that off.login logic is actually what's happening here. If you notice, every single logic concerning checking the database if this user exists, if we scroll down, creating the JSON web token, returning that JSON web token back to the web server that is using our function. All of that authentication logic is happening in this function. We're separating logic to the logic that's rendering whatever this function is creating. And that's basically one of the most important things we have to do in functional programming. A lot of people, when they take programming 1 and programming 2, a lot of their methods and functions are doing system out print lines in places they shouldn't be doing that. If you want to emit something out of your program, or you want to accept inputs into your program, they should be relegate it to a single piece of your code base and restrict them to that piece of your code base. Let's go to the next example. So data is immutable. So immutability basically means that whatever piece of data that's handed to you, you shouldn't mutate it, you shouldn't change it. You should give back the same piece of data that you borrowed from someone. So it's kind of like having good manners. Kind of, you have to give back to someone whatever they lent to you in the same condition. You shouldn't, like if someone lent me a book, it would kind of be rude if I like decided to tear up some pages, you know, destroy some parts of the book. So it's the same kind of a principle in this slide. So if we go to the code example. So this gets a bit complicated. So let's do a zoom in. So in this function, I'm receiving, forget about the complexity of this again. All that you need to know is that this function gets a list of tuples, and I'm returning a list of tuples. A tuple is basically a 2-element array, and then within this 2-element array, I have a string, and I have a string. This is also a string. I just called it tag. What I'm basically doing here is, based on this tag, I'm getting whether it's a noun, a pronoun, a verb, or an adverb. I'm using that to judge how important this string is, but you can ignore that portion. What's the key takeaway for this is the fact that, where is it? If we scroll down, let's scroll down. If we look at this reduce function, right, I'm accepting the ner tuple list. So if we scroll back up, scroll. So I'm getting this list, I'm getting this array of numbers. Someone gave me the responsibility, someone lent me this array of numbers, but I don't want to destroy whatever they lent to me. I want to make sure that I don't change any elements within this list. So instead, what do? When I scroll down, instead of mutating that list, what I instead do is I actually return a new list, and that's what the reduce function does. We'll cover this later on in the slides. But what I'm returning here is basically a new list. And that's what you want to do with functional programming, is that instead of me mutating the array that has been passed into my function, you should instead return a new array. So if someone passed to me a string, right? Like in Java, this is Java does this under the hood. But if someone passes me a string as a parameter, I should return back a new string. Java returns a new string for you automatically. But if you mutate that string, that's a bad practice, because unexpectedly, if someone passed that string in as a parameter and I change it without them knowing it, in the latter parts of the program, when they expect to use that parameter, it would have a different value than the expected value that they have. So make sure to not destroy the data that's kind of been handed to you. No one's lost yet at this point? Everyone's fine? Okay. Let's switch to the next slide. Expressions instead of statements. So you guys know if statements, while loops. So in statements, you have lines and lines of code. You're basically telling the computer how to behave using these lines and lines of code. So you're telling the computer how to do things, but in functional programming, we move from telling the computer how to do things to telling the computer what kind of outputs we want to receive. So it's a higher level of an abstraction. Let's move to the next slide. So this is another Haskell example. Again, don't get bogged down with the details, but all I want you to pick up from this is the fact that this entire line right here is a statement, and this entire line here is a statement, and this entire line as a result is a statement. So this is a statement, and this statement is used within this statement, and this statement is the value of this function right here. But in a general sense, this entire thing is a statement. So you want to avoid having, I'm sorry, I meant expressions. Everything here is an expression. So this is an expression, this is an expression, and as a result, this entire thing is an expression. You want to avoid having statements, and in Haskell, they basically prevent you from having statements.
So right there, you're doing pattern matching, right?
Yeah, exactly. So Adam brought up a good point about pattern matching. You see this in a lot of functional programming languages, where I'm receiving this kind of an object, and this object has certain properties, certain attributes, and certain methods within them. Functional programming basically allows me to inspect those pieces of the object really easily too. Going beyond that, this is an expression, this is an expression, and this is an expression. So if we actually inspect this, if we ran this in a console, this emits a value, this emits a value, and that value gets stored into this function definition. And then in the general sense, this entire thing is an expression. So is anybody lost about this one? No one's lost about this one? Okay. So let's jump to the next one. So you'll learn 3 very important functional operations for functional programming, and that'll be map, reduce, and filter. We'll go into more in-depth examples for that now, so let's proceed. So what does a map operation do? A map operation, it accepts a list, and it returns back a list. So I'm getting an array, and I'm returning back an array. What a map operation does is, it's a function that tells me how I should transform every individual element that I'm receiving to the list that I'm returning. So for example, I have a list of circle elements, and I want to get back a list of diamond elements. I have this mapping function that tells the computer, hey, I don't care how you do this, but I want you to turn every single element that you're giving me into a triangle object. And that's basically what map allows you to do. Is it's a mapping, you get back you get an input. I want to get a specific output on that individual input. So this is an example of a map operation in JavaScript. So say I'm getting an array of numbers, right? I have an array of numbers from 1 to 6, and say I want to increment every single number by 1. I have a function here where all I'm stating is I'm receiving some number, an individual number, and what I want to do to that individual number is I want to add 1 to that number. So that's all I'm doing here. This function here is getting applied to every single element within this list. That's why as an output we get back 2, 3, 4, 5, 6, 7. Because you're doing a function application, so you have x plus 1, so you have 1 plus 1 becomes 2, 2 plus 1 becomes 3, 3 plus 1 becomes 4, and so on and so forth. And here we have another example where instead of adding 1, we're concatenating t to every single string within this list. So I have this list of elements, right? I have kappa, ma, and ra. That function gets applied to every single element within this list, and that function is concatenating t to every single element in this list. So as a return value, I'm getting back cat, fat, mat, and rat. All I'm doing is that function over there is adding the t in the string that I'm receiving and returning back that element as a result on the list that I'm obtaining. Another example is with booleans. All I'm doing is I'm receiving a boolean. I want to flip that boolean. So I'm receiving a true here. It gets converted to a false. The false gets converted to a true. Filter. So what a filter does is, unlike a map, it also accepts an array of elements. But instead of map, in a filter, you have to return back a boolean. And what a filter uses that boolean for is when you return true, it lets it lets the filter operation know to keep that element, and if you return false, it should not keep that element. So for example, in this filter function, you see that I'm only accepting circle elements. As a result, I'm only receiving back a list of circle elements, and I'm ignoring this element, and this element because of the fact that they're not circle elements. I'm only accepting circle elements. So if we switch to the next slide, we have another set of examples here. So let's say I am obtaining a list of strings. There are strings of all kinds of sizes, but I only want to get strings of sizes that are greater than 3, so 4 or greater. I specify a filter operation here, this filter function. It accepts a string, x is a string, and it returns back a boolean. So if you're greater than 3, you're returning back a true. So if you notice, what happens is every single string that's less than or equal to 3, that has a length less than or equal to 3, is actually not getting emitted back on the list that we're returning. So for example, cat. Cat is a string of size 3. It's not getting returned back into here. Another example, we have a list of numbers. Let's say I only want to keep numbers that are greater than 3. Again, I have a function here that's telling me, hey, I'm accepting a number, I'm getting a number, and I'm returning back a boolean, because x greater than 3 returns back a boolean, a true or a false. Based on that expression, that tells the filter operation what numbers I should be getting back. So in this case, notice that I'm not getting 1, I'm not getting this one as well, because they're all less than 3. Whereas 5, 7, 8, 9, and 5 are greater than 3. That's why they are getting back. This is a more complicated example of the filter expression. We can ignore this, I think, because it's too complicated. The reduce operation is actually what's known as the God function operation, because using reduce, you can actually make map and you can make filter out of them. So if you want to make map and you want to make reduce, but you map and reduce. You want to make map and filter, but you don't have those functions. With reduce, you can simulate those operations. So you can ignore this. This looks complicated, but what a reduce basically does is I'm getting an element, and I'm adding that element into some sort of an accumulation. You typically use reduce when you're summing up things on a list. So we have an easy example coming up on that. So let's say I want to add all these. So I'm going to get back a value 14. If you notice, I'm getting my reduce operation. The function that I'm giving to my reduce operation accepts a current parameter and an accumulated parameter. And as a result, I'm returning back some value. What accumulated does is, as this reduce operation continually applies the function, what I'm actually doing is I'm keeping track of the accumulation that I'm making, and that accumulation is whatever is the return value of this. So for example, let's start with the first element. My accumulated would be 0 because I'm starting at the beginning, and my current would be 1 because I'm working on the 1 element. 1 plus 0 would be 1, so my accumulated would be 1, and my current would be 1 when I move here. And it just keeps adding it up and adding it up and adding it up and adding it up. The same thing here. If you notice, I'm doing the same operation, but instead of integers, I'm doing it with strings. All I'm doing here is I'm concatenating all the elements of this string, list string. So kappa, ma, ra gets concatenated together to one string. Is anyone lost about what this reduce operation does? No? Yeah.
So basically, the 1, 2, 3, 4 is 21. Reducing takes one element at a time
So this accumulated right here, what's happening is it's getting initialized to 0, right? So I have current, which is 1, accumulated, which is 0. 1 plus 0 is 0. And then I move in here. Accumulated is so far 1, right? And I have 1 here. So 1 plus 1 is 2. And then my accumulated is 2, and this is current is 3. So 3 plus 2 is 5. And then it moves in so forth. So I have an accumulated of 5, current of 4, that becomes 9. And then my accumulated is 9, my current is 5. 5 plus 9 is 14. So that's how I'm getting this. The same thing here. My current is ka, my accumulated is an empty string, so ka plus an empty string is just ka. My accumulated is ka and my current is fa, so it becomes ka fa. My accumulated is ka fa and my current is ma, so it's ka fa ma. And in here, my accumulated would be ka fa ma, my current would be ra. So the return value of that would be ka fa ma ra, and that's why I return ka fa ma ra. Yeah.
So for accumulation, it's always, when first doing it for accumulation and recurrent, the accumulation is always size 0 of that particular primitive.
So yeah, so for JavaScript, you can actually, I didn't place this here, but you could actually specify like an initial empty accumulation value. So I could have said current accumulated 0 because this is a number list, and here I could have said current accumulated and then empty string, but I removed that out of simplicity. But yes, that is correct. Like in JavaScript, JavaScript is kind of intelligent enough where it kind of knows that this is a string, so it assumes that your starting accumulated value is the empty string, and so on and so forth. So, okay, so let's go back to this slide. Okay, let's go back to the red slide. Yeah. So why are these operations important again? If we go to map, let's go to map. This is an important operation because you're not telling the computer how it should go about iterating over this array and changing every single individual element of the array. You're letting the computer do that for you, and instead you're telling the computer what you want to be done on every single element of the array. Now, that's a very cool and important thing because what if, for example, instead of doing a simple addition, right? Instead of just adding 1 to every single element of the array, what if, for example, I'm given a URL here, right? So instead of getting a list of numbers, I'm getting a list of URLs. And I want to do some complex processing on every single web page that's on that URL. This map operation would take a lot of time, but what the computer, the programming language, and the interpreter can do underneath is it can spin this operation up in one server, it can spin this operation up on another server, it can spin this operation up in another server, and so on and so forth. That's actually how Google does a lot of their search engine functionalities. They came up with a research paper back in 2003, 2004 called the MapReduce paper, and a lot of cool stuff came out of that research paper. They primarily used it to count, what do you call this? They used it to count the frequency of words within web page documents, and then they used that to kind of rank how relevant a web page is to a search term that you're making. So imagine Google running, they have a list of billions of URLs, and for each individual URL, they want to process each individual URL and calculate some complicated process on each individual web page document for that URL. That would take a lot of time if they're doing it sequentially. The cool thing with map is that you can let the computer decide for you whether you want to do this on a one-core computer or do this on separate threads or do this in separate processes so that you can take advantage of the parallel cores of your computer, or you can even split it to another server. You can send this operation off to one server, you can send this operation off to another server. It's a really cool thing. In the same way, filter, again, you can actually run this operation in a very concurrent way. So you can split this operation and send it to one server. You can split this operation and send it to another server, granted that the operation is complicated. And all that server has to give back to you is whether it got back some element or it didn't got back some element. So, yeah.
So the reason why you can spin it is because every index is returned separately?
Yeah, every element is returned separately. So if you notice, if I was coding this in a normal way, right, in a non-functional way, instead of using these map, reduce, and filter operations, I would use some kind of iteration. So I would do for int I equals 0, and then I is less than the size of the list, then I plus plus. Then after doing all of that, I'm accessing the value in that index and mutating it somehow. If I did that, that kind of constriction wouldn't allow me to scale. Let's say my manager comes up to me and tells me, hey, I want you to change that code so now it works across our cluster of 1 billion servers. I want this code to take advantage of that 1 billion servers that we just bought for some reason. That wouldn't be trivial because you're constricted to the fact that you wrote a code that's based on iteration. Whereas with functional programming, you're letting the computer handle those nasty details for you. Instead, you're telling the computer, hey, you know what, I don't care how you do this. Instead, I'm just going to give you this function, and that function will run an operation on every single individual element. I don't care what my inputs are. I don't care what my outputs look like. I just have the specification. Do the operation as you please. So that's one of the cool things with functional programming. If you guys go into depth with Java 8, in Java 8 you can actually specify, Java has an array utils map operation, and you can actually specify to Java whether you want the operations that are happening in that map operation across separate threads or across several processes. And that's a really, really cool thing. You can use the power of quad-core computing.
So in Python, the lambda function works like that, right?
Yeah.
Do they have different names for filters?
Python has all three functional. So Python 2 has map, filter, reduce. Python 3 got rid of, I believe they got rid of filter because they said that it looks nicer to just have a regular for loop with an if statement. But yeah, you have all those functional things in Python.
But map would be called lambda, right? Or they have
No. So there is a function called
it
map.
is. Okay.
Yeah. If you want to use, like Josie said, if you want to use the functions that they remove, what I use is in Node.js, since I code so much in Node.js, I use Lodash in Node, but in Python you have PyDash, and it gives the same functions. So they have map, reduce, they have apply, concat left, concat right. They have all these operations. So how many of you guys have heard the solid principles? So maybe you've heard the solid principles. So this is really important in object-oriented programming. They have the single responsibility principle, open close principle, so on and so forth. You might say these principles only apply to object-oriented programming, but they actually apply to functional programming as well. So if we look at this, what this is basically saying is whatever piece of code that I write, so for example, whatever piece of function that I write, that function should be as small in its scope as possible. So earlier when we were looking at that credit card validation function, notice that every single function within that bigger function took care of a very simple thing. One function doubled every other element within the list. The other function, all it did was sum up every single number within that list. That's all that this principle is saying. It's saying that you should only your functions should only focus on a very small set of things. Open-close principle, all it's saying is, if I mutate a function, if my smaller function's code definition changes, me changing that smaller function shouldn't cause me to change the code on the bigger function. So for example, if I change that double every other implementation, let's say instead of doubling every other element in the list, I want to do that but across several processors. So I'm going to add some new code to manage the fact that I'm going to split the computation up in parallel processors. The definition of that function shouldn't change the definition of the credit card validation function that I'm using in Pendency. List of substitution, all this is saying is that if I have a function that has the same type signature, so say I have a function that accepts an integer and returns back a Boolean, I should be able to use another function in its place that has the same type signature. So say I have a function and that function accepts a function that does some sort of a mutation on a list. So I'm giving that function a list and I expect that function to give me back a number. I don't care how that function handles that list. I only care about the fact that I'm giving it a list and I'm getting back a number. List of substitution tells me that I can switch whatever function that does that operation, and because of the fact that it respects the same type signature, I shouldn't be changing the bigger function's code definition. Interface segregation principle kind of goes hand in hand with list scope, so I'm not going to go in depth with that. And the pendency inversion, what the pendency inversion states is that instead of me depending on global variables and on global functions, instead I should be passing the functions and variables that I need explicitly into the function, so that in essence it would be way easier to test your code. So for example, I have a piece of code that accepts, I have some function that connects to the database. Instead of that function, what do you call this, referencing some global variable about where my database is, where what my database port is and database URL is, instead of depending on that global variable, I should be passing those explicitly as parameters into that function. That's all what that means. So yeah, if we go to the next one. So we're going to be going to specific code base examples, so I can give you guys more a more refined taste of what functional programming is. So let's go. Let me go show them.